on the way. But I'm Brian Bargenbrook. We've got Chris Sanders here as well. We're both from NWS Topeka. What we're looking at today is operational forecasting of freezing rain and also the associated impacts from ice and wind. Some of you may have seen at least parts of this, especially if you're involved in the Central Region Forecast Builder or if you attended the recent NWA conference out in Norfolk. But we're also adding some other things, and we wanted to give people a chance to ask questions too if they had any. At this point, we're just going to dive right in. We'll hit on several aspects of our freezing rain research and where we're going in the future, and again, give chances to ask questions if you have any. There we go. All right. So as far as motivation, it's probably pretty obvious. You know, freezing rain is a huge impact. Whether you get just a glaze on up to an inch of ice, it's just massive impacts on travel and then also on infrastructure. Accurate ice forecasts are something that are difficult. They're very difficult to make. It's such a narrow window of opportunity to get accumulating freezing rain. But one of the questions we've had is you know, there seems to be some lacking research. Some of the research out there maybe wasn't focused on the weather side of things and the prediction. So we wanted to jump in and address that. Speaking of that research, there were a few studies out there that looked in depth at ice forecasting. Jones, which many of you are probably familiar with, in '96 and '98, out of the Cold Regions Research and Engineering Laboratory, they did a basically overarching work on all this. Society of Civil Engineering deemed this work to be the culmination of prior studies into a single quality ice load predictor. At the same time, lacked a robust climatological database to run off of. A lot of it was based in physics, which you'd think would make sense, but from a meteorology standpoint, we can improve that. Also, it was only verified with just a handful of icing events. And finally, the simple version of this that can conceivably be used in a prediction aspect, it made some assumptions of physical relationships that probably decreased its utility as a forecast model. For instance, it assumed that temperature is always below freezing and has no effect on icing, and precipitation rate was used to estimate liquid water content of the air. We found some things that were quite to the contrary of their assumptions there. So when it comes to ice accretion efficiency, we wanted to know, do the meteorological elements that are commonly measured and forecast, for instance, air temperature, precip rate, wind speed, etc., do those elements affect ice accretion efficiency? And then furthermore, would the effects of those variables be represented in the ice to liquid ratios during freezing rain? And ice to liquid ratio is a term you're going to hear a lot through this topic. It's the same concept as snow ratios. It is during certain meteorological conditions, how much of your liquid is going to be realized as ice accumulation. The beauty of this is that, and really what drove it, is this little icing sensor right here, the freezing rain sensor on the ASOS. It's been in existence for a while, but it's been tested robustly, and now finally in the last few years it's been turned on at numerous, almost all ASOS sites across the country. Our data and method involved using the 5-minute observations from the icing sensor. Again, this was disseminated in a widespread nature by late 2013. At that time, there were 650 icing sensors operational, and we wanted to note too, this is a geographically diverse data set. That's why we tried to include offices from across all areas of CONUS on this, because it applies to about everybody. How the sensor works is it vibrates as ice accumulates, and once you get more and more ice on there, the vibration decreases in frequency. So kind of a neat little relationship. What it was tasked to do when they created this was measure flat, elevated surface accretion. ASOSs are at airports, and they wanted to relate this to aviation concerns and plane accretion, things like that. The good news is we can draw a direct correlation even to radial accretion from that. There's a melting cycle over every 800ths of ice accretion on the sensor, and this sensor itself was officially tested with more than 1,500 hours of icing. So it's, again, robust testing, and they didn't just throw it out there. There are some limitations that can cause minor errors. One of those being a slow de-icing recovery if the temperature is near freezing. Again, it de-ices every 800ths. And there are a few others too, but they occur in a very small percentage of situations with this ASOS. A little more on this process here. When they tested the sensor, they measured ice mass and thickness on racks and horizontal plates just above the ground. So when they did this, they gathered data pairs to compare both the ice mass that they measured here, that they actually physically measured, to the frequency change on the ASOS icing sensor. The correlation coefficient between the frequency and ice mass was 0.98. So really, really strong correlation. Again, what we're trying to push here is that it's a quality sensor. It makes sense what they're measuring here. From that point on, again, what the sensor measures is elevated horizontal ice thickness, and that's what you see in the top left here. I just want to point out that, again, there's a direct correlation when you're transferring that from horizontal thickness on an elevated surface to a radial thickness around a branch, and it's approximately 40% is what they found based on their large amount of data and evaluation. Also, I'll make a note here that there are different ways to measure ice, and this is something we need to address in the near future in the National Weather Service. There are different ways to say how much ice is going to accumulate, and we need to be very specific when we're doing that. But I'll just leave it at that at this point. But just know that there are different ways to measure. Excuse me. So getting back into our data, we focused on freezing rain and freezing drizzle, but if it was drizzle, it had to be very heavy. We had to get at least 200ths per hour of liquid precipitation. Again, sorry, skip back here. This was the winters of 2013-14 and 2014-15, and you can see the locations across the CONUS where we gathered data from during those periods. The size of the circle correlates to the number of observations from each location. What we looked for was 60-minute periods with continuous freezing rain or freezing drizzle as a weather type. There could be no mixed precipitation in there. Again, the 60-minute liquid precip had to be greater than 200ths or equal to, and the 60-minute icing did not allow trace amounts. It had to be at least 1/100th of ice accumulation. On that, we used the 5-minute obs, so there was no requirement to begin or end at the top of the hour. It could start at 20 after, as long as it was 60 consecutive minutes. And then the other meteorological variables were averaged over that 60-minute period with all the 5-minute obs included. This resulted in 1,255 total 60-minute periods of ice accumulation. That's what our database was comprised of when we look at these things. When it comes down to results, you know, just up front here, if you'll notice the horizontal kind of teal colored box here, the ice to liquid ratios were generally less than 1-to-1. This is important in its own right because a lot of our forecasting techniques, we've just, you know, gone with 1-to-1. Even simple physics says that the density of ice to the density of water should be like 1.1-to-1. But the reality is that we have runoff and we have things like that that negatively impact it. So if it rains an inch, odds are more than likely you're going to have less than an inch of ice. That's a very important thing to take away. Also, we wanted to point out when we discussed the different ways you can measure ice, you'll notice the radial box and whiskers on the right in the green. There's no interquartile overlap between the measurement of horizontal ice thickness and a measurement of radial ice thickness. And so again, it's very important that we be specific about what we're forecasting to these key users outside of the National Weather Service. Another interesting finding here, when we gathered all 1,200 of those observations, and this might come as no surprise, but freezing rain was more likely to occur at night. A lot of this is probably due just to diurnal flux of shortwave radiation, surface temperature trends, things like that. You'll even notice there's a minimum in the afternoon, and we tried to highlight roughly, you know, the daylight hours with the yellow there. Basically, nighttime just has an environment more conducive to ice accumulation. As far as what we examined independently, we looked at air temperature, precipitation rate, wind speed and wind gust, wet bulb temperature, and relative humidity. We looked at all these things to see how they might impact freezing rain accumulation and ice to liquid ratios. A few of the things we found, this is extremely important here, is precipitation rate had the highest correlation to ice to liquid ratio out of all the examined elements. Basically, if it rains harder, you get more runoff in the majority of situations. So again, this is the most important and the most direct correlation. Furthermore, wind speed and gusts, they had a similar influence on ice-to-liquid ratio when comparing the two. But we used wind speed when we were going forward here in our analysis because gusts are generally infrequent over long periods, and we were looking at 60-minute duration. The impacts were, again, similar, and we'll get into exactly what those impacts were shortly. Air and wet bulb temperatures were both examined, and they also showed similar trends, but the correlation was greater for wet bulb. A t-test proved that wet bulb had less error as a predictor, and so we went ahead and used that, and we'll get into one other reason why we use wet bulb temperature in a little bit here too. Finally, we also evaluated relative humidity, but it had little to no effect, especially as a standalone variable. All right, so let's get into some numbers here. This is with, again, over 1,200 hours of ice. And you'll notice here the effects of precipitation rate. On the left, you're looking at a rainfall rate, liquid, of 0.02 to less than 0.05 inches per hour. And you'll see that the mean there, the median is 1-to-1 for those types of light rain situations. When you get even lighter events, it can go a little higher, but that may depend on things like temperature and wind speed and so on and so forth. The real takeaway here is that when you get into the heavier icing events, precip rates greater than 1/10 of an inch per hour, you're actually looking at more than likely an ice-to-liquid ratio of 0.5 to 1 or less, especially when you get up above 1100ths per hour. So this is something important to take in. If you're going to have that inch of rain, there's a good chance you're going to have significantly less ice actually accumulating. When it comes to wind speed, there was only a minor response at low wind speeds, but once you got above 10 or even 12 knots, that's when you started to see things increase as far as ice-to-liquid ratios, especially when you get above 15 knots. And there weren't a ton of instances of that occurring in our database, but there's definitely enough for a signal that when the wind speed increases, your icing efficiency increases. And that is especially related to things like removal of surface heat from the drop as it's freezing. Finally, the wet bulb temperature, you get your highest ice-to-liquid ratios generally in the -2 to -3 Celsius range, even -1 down to -3. Once you get on the very cold side of this, you may start to mix in some ice pellets or something like that. But generally speaking, if you want a very efficient icing event, you're going to aim for a wet bulb temperature in that kind of -1 to -3 Celsius range. Another important thing to notice here, and we'll point it out, is that when you get above 0 for the wet bulb temperature, there are almost no instances of freezing rain. But when you use just the air temperature, there were many instances of freezing rain occurring with an air temperature greater than 0 Celsius. It doesn't always happen, and we'll discuss that a little bit more, but a key takeaway here is that even with an air temperature of, say, 33 or 34 degrees Fahrenheit, you can occasionally have freezing rain accumulate. All right, so a few notes here. Again, we want to push this hard. Increasing precipitation rate likely leads to more liquid runoff due to the short amount of time that liquid needs to freeze before more liquid is added to the ice surface. Increasing the wind speed promotes evaporational cooling and supplies cooler air temperatures to the near the surface of that ice and that liquid drop. Also, decreasing the wet bulb temperatures will help offset the heat fluxes, like latent heat fusion, and it promotes evaporative cooling near the surface. Other interesting findings. Again, freezing rain more common overnight. Again, we had only 56 hours of icing with an average sustained wind greater than or equal to 15 knots. That's not very much, but it does happen. And Chris is going to talk about the impacts of that a little bit more as we go on, too. And then finally, one of the big takeaways here was that there were 403 hours that had an average hourly temperature greater than or equal to freezing, but freezing rain was occurring. Of those 403 hours, only a handful had a wet bulb temperature greater than freezing. So here's the takeaway here, is that when temperatures above freezing, you can get rain or freezing rain. But you must have a wet bulb temperature less than 32 if you want to get that freezing rain to occur. All right, so what do we do with all this data, right? We put it into a model, and again, especially those in Central Region, you've probably heard of the FRAM. It's being involved in the forecast builder, but for anyone else who's not as knowledgeable on the topic just yet, we'll go into it in a little bit of depth here. How it was developed was basically we used various transformations on each predictor variable in order to linearize the data. The preferred transformation model for each element was determined by the greatest correlation of determination. A lot of statistics going on here. We then used a forward selection stepwise regression so that the most significant terms were used. But then, and this is important, everything had to be meteorologically reasonable. So if statistically it wanted the line to curve back up at warmer temperatures, that just didn't make sense, so we would cut it off. All of this passed the watchful eyes of weather and forecasting as far as statistics go, and so we're stepping forward with it. Here's how the actual regression models lined up for each of our elements, and you'll see they line up pretty well with the mean values and all within the box and whiskers. Nothing surprising here. When the wind speed increases, the ice-to-liquid ratio increases. When precip rate increases, the ice-to-liquid ratio decreases. And you'll see that peak in ice-liquid ratio for wet bulb temperature, about right around -2 Celsius. After that point, we got to talking and wondered, well, you know, precipitation rate had the highest correlation. Is it more important than wind or wet bulb? And so we went through and we gave each element a weighting function, and then we did a reverse forecast against all of our observations. The one thing I do want to point out here is that when we were developing this model, we only used 1,161 of the observations, and that's because we needed a control group to test against when we came back around to see if our model was worth a darn. The combination that produced the lowest mean absolute error was deemed the optimal weighting combination. And here is the freezing rain accumulation model. All right, there are situational dependence on this. When the wet bulb is warmer than 0.35, then different equations are worth more. But this isn't terribly exciting to read, so I'll pass it on. The good news is this is the FRAM that we used to forecast ice. Now let's test it. All right, so we again extracted 20 randomly selected freezing rain events to use as a control group to test against to see how well this model would perform. An event had to be more than 3 hours, no temporal gaps. For it to be an event, it had to occur, you know, without any pauses that lasted longer than 12 hours, and each site had to be at least 300 kilometers apart or differing in date. These 20 events added up to 94 hours of ice, and the total accumulation for each event ranged from 5/100ths to 57/100ths of ice. So again, a wide range of events here. Finally, we evaluated it next to the Krell simple model, Jones's work, and then also just compared it to a simple 1-to-1 ice-to-liquid ratio, which is commonly used. Here's a little zoomed in value here. The black line indicates a perfect forecast. And so the values that are closest to the black line indicate a better forecast for that given amount of ice. The takeaway point here, and what we were happy to show, is that the FRAM in the blue squares performed quite well, especially when you got above 1/10 of an inch of ice that was observed. That's when you had the 1-to-1 ratio, and the Krell simple model had a tendency to over forecast. Here's another way to view this. This is for each of the 20 test cases, and this is a display of absolute error in inches. Again, the takeaway here is that the blue lines are smaller, and so the FRAM performed quite well. And in fact, the FRAM ice predictions were superior to all their methods for 17 out of the 20 randomly selected events, with a mean absolute error of only 0.046 inches. Again, the Krell simple model and 1-to-1 ratio tended to overestimate ice accumulations, especially with the higher impact, higher amount events. All right, so that's how we developed the model and tested it. Now let's talk about how to use it a little bit. I'll focus here first a little on the Central Region Forecast Builder process. In here, what you really want to do is focus on the base grids, the temperature, the wind speed, the dew point, the precipitation and QPF grids. You know, when it comes to mixed precipitation, that's handled by the probability of weather type methodology, which will split off the QPF according to the likelihood of various types of precipitation. So you don't have to worry about making manual decisions that way so much. especially as long as you work diligently on putting some great base grids together. When you're creating the ice amounts, the FRAM runs automatically within the forecast builder. It generates hourly ice-to-liquid ratio grids based on the FRAM method and associated base grid inputs. And then it uses those to generate an ice flat, which correlates to the NDFD elevated flat surface, and then also an ice line grid, which is a radial equivalent used for DSS and other various things. Those are, again, based on the QPF devoted to freezing rain and the determined ice-to-liquid ratio. Again, the main takeaway here is just to really focus on nailing down those base grids, and the rest that comes out should do pretty well. For the non-forecast builder offices on the call here, the non-central region folks, there is a tool available via the FCP, and it's the Freezing Rain Accumulation Tool, or the FRAT. Sorry, we're throwing around two different algorithms here, or two different letter combinations. But go ahead and, if you'd like this, search the FCP for the FRAT tool. Special thanks to Eric Weiss for helping develop this. When you're using this, you should expect the most favorable results during freezing rain, although it will forecast for lighter freezing events as well. So that's just something to pay attention to. Keep in mind that this was developed with, liquid rates at least 200ths per hour. The input grids that it uses are the temperature, wind speed, dew point, that combines to create a wet bulb. You get a weather grid, QPF pop, and or probability of type, which I guess we could remove that for those non-forecast builder offices. The output grids, again, are an hourly ice accumulation, hourly ice flat, hourly ice line, and then it all adds up into the ice flat and ice line accum. When it comes to the NDFD, you're using your elevated horizontal flat ice. Here's what the GUI looks like in that tool if you're interested, and I just wanted to make a couple notes here. With the precipitation rate being so important, it's important to realize that having 6 hourly QPF grids can be deemed a little bit of a limitation. So if you can break them down into higher resolution when it's possible, especially when you get into the shorter term, then that's going to be beneficial to your forecast. On the other hand, if you want to select the nature of the precipitation, so if you expect convective precipitation versus just a long, slow, steady rain that has the same rate, you can make a selection with this slider bar here. It defaults to the 50%, but go ahead and give that a read if you're using this tool, and you can probably improve your results based on that. Also, because this isn't a probability of weather type tool, mixed precipitation areas will be handled by you. And so if you want 80% of your precip in a freezing rain mix to be devoted to ice, then you can work on that here. If you have any questions, feel free to email us and we'll work through it with you. But that's just an example of what we've got. A couple other notes: icing during near freezing conditions. You may have some uncertainty in your temperature and dew point forecasts. I know mine are never 100% perfect. And that can give reason for some questions of your weather type between rain and freezing rain. Both ice accumulation and just rain have been documented, when wet bulb temperatures are below freezing and air temperature is greater than freezing. Rain remains the most common in this scenario with temperatures warmer than freezing, but we'll reiterate this again, freezing rain can occur if the wet bulb is colder than 0 Celsius, or less than or equal to, Some preliminary evaluation shows that about 30% of the time, if your air temperature is 33 and your wet bulb is 32, you'll get freezing rain out of that scenario. Another thing to keep in mind is that you should be aware of pre-existing surface conditions. If your temperature overnight was 20 degrees and you're doing a gradual warm-up, your surfaces are going to be sub-freezing and you will more readily get ice to accumulate. Then we'll run to icing on roadways. The FRAM is not intended for this. On roads, you're basically looking to get rid of friction. You're not looking to bring down power lines or anything. It only takes a small amount to go from no impacts to huge impacts, and I think we're all aware of that. When we talked to our Kansas Department of Transportation here, they said total ice amounts are not as important as location, coverage, timing, and duration. I think that's an important takeaway there. And when you're actually doing this forecasting, again, the FRAM doesn't necessarily apply. You want to look into things like the surface air and soil temps, solar insolation, is it an elevated or non-elevated surface? Is it the first event of the season or the last, where there's tons of chemicals on the road? Things like that. So these are all things that we don't necessarily forecast, and that makes it tricky for roads, but we can sure provide some insight to those users. All right, so I'm going to take a break at this point for some questions. I'll try and unmute you all if you do have questions, and see how this works. This is my first time actually running a webinar like this in terms of getting people to talk or not. So if anybody has any questions, let's give it a shot. Let's see here. Well, it seems I may not have the ability to do this. John Ice, if you're on the call here, are you able to unmute anyone? Or unmute everybody? Oh, I hear somebody, so something must be happening.
Hello from Oberlin, Ohio. Oh,
all right. Well, hi Ohio. Hello from Kansas. Well, anyway, one way or another, if anybody has any questions, fire away. Otherwise, we'll move on to the next segment of our talk here on impacts.
Of course, the question comes to mind with some of the older observations, potentially, in the absence of the ice-free wind sensor, how much of the data for the wind speed might be contaminated.
You know, the good news here is that at the point when these icing sensors were turned on, the ice-free wind sensor was in effect. It should have been implemented at all of these sites. So good news is we did not have any missing wind data that went with any of this. We didn't mention it in here, but if any data were missing or were bad from a temperature, dew point, wind standpoint, they were immediately thrown out.
Okay.
All right, any other questions at this point? All right, well, I will hand it off to Chris, and we'll have another opportunity at the end to chat if you all like. All right, Chris, go right ahead.
Awesome, thanks, Brian. All right, so, did that not work? Go for it. Okay, so now we're going to focus on the impacts from ice and wind, and basically what we wanted to do here is come full circle. We have this tool in development, you know, hopefully in a more accurate way of predicting ice. It's all related to the ASOS sensor that Brian talked about. So we wanted to somehow relate impacts back to this sensor. We have the sensor all over the country. It's a subjective measurement of ice, and so we're able to find some consistent signal in the measurements of ice and then go back and relate that to the impacts and hopefully come up with something there. So obviously, you can have ice accretion on the transmission towers, utility poles, regular power poles, power lines, and then tree branches. A lot of the power outages that are experienced during ice events are from tree branches, either disrupting power lines or taking down poles and things like that. So once you accumulate this ice, structurally integrity becomes compromised as the object experiences added stress, and then wind, you add wind to that, the stresses will only increase on the ice-loaded object. So then you start to get structural failure. So Brian touched on this a little bit, and I'm going to focus on it slightly more. So again, we want to relate these impacts to the ASOS sensor, the flat horizontal ice thickness. But that conversion, about 40%, can be related to the uniform radial thickness. Again, that is very important when you think about power lines, and tree branches are cylindrical, so that basically the radial thickness is related to that. And so you start to throw around thresholds and actual what point do some of these tree branches and power lines come down? What thickness are we working with here? So, and when you actually focus on the radial thickness in more depth, you can have basically a uniform measurement, which in nature is hard to get. Usually you get some non-uniform here to where some of the ice might build up more on one side of the object than the other. almost to the point where all the ice is gathered here on one side of the object, completely non-uniform. Here's some of the physics that we've, through some of our literature review, has found that might contribute to this. You get more of a wet growth versus a dry growth, and then a variance in the horizontal flux, or sort of the wind flux there going on. That becomes important where maybe you get a call here, spotter calls in, says I got an inch of ice. Well, what kind of inch of ice? Is this a uniform thickness? Is it a non-uniform thickness? So I have an example over here where maybe if it's non-uniformal, they call in, they have an inch. Well, in terms of weight, that is not equal to what would be a uniform thickness of 1 inch. And actually drew these shapes to be proportional, and you can see how different they actually are and what the actual ice on the ASOS would measure with these certain thicknesses above them. So you see quite a bit of difference going on there. So it's very important if you either get a picture, some sort of description of what people are measuring. So in terms of weight, this 1 inch non-uniform thickness is actually, in terms of weight, related to, again, more like a ½ inch of uniform radial thickness. So a couple examples, easy way to get around this, of course, is measuring the entire branch and ice, subtracting what is the estimation of the branch or whatever object. So then you're left with the total ice, and then dividing that by 2 will give you the uniform radial thickness. And again, that can be related back to the ASOS, which again is measuring basically a mass per unit area. So you can see for some of these events, the typical liquid, and this is based on some of the results that Brian talked about earlier, just on the, I think I used the median ice-liquid ratio for some of these. Here's some even greater thicknesses. So you're looking at when you have a radial ice thickness of about 1.5, and this is all estimated. I'm just trying to go off the soda can there, but it takes about almost 5.5 inches of actual rainfall to liquid to produce something like this. And of course, wind will play a role in some of this. There could have been less if the wind was higher and things like that. But you're looking at a substantial amount of rain to produce these really big thicknesses. So these are kind of rare events that happen, I think, from what we've seen. So then I kind of get into what, the grids. Brian explained, what NDFD is as of now is using the flat ice. It's what the ASOS is actually measuring. We can use it for verification, so that's great. But look at some of the definitions and under the directives, and as of now, the 6-hour ice accumulation is the expected average on all exposed surfaces. So maybe now at this point we can maybe start to be more descriptive of the 2 different thicknesses or pick some thickness to move along with that for the future, again, or maybe one of them can be used for maybe DSS purposes. When you think about an ice storm warning, the old classic 1/4 inch or greater, we think about branches coming down, power lines. Is that applied to the radial or the horizontal thickness? So those are some of the things that Brian wanted and I wanted to answer, moving ahead and looking at some of this data. So here's a storm here that happened back in 2007, January, at the Springfield Weather Service office. This was a measurement taken right outside the door there. And so we break it down, and it came out to a radial ice thickness of just under 1/2 inch in the liquid. Based on our results, it would be about 1.7 inches. So I went back and looked at the actual observations and found that the liquid was just slightly higher. There was some actual heavy rain involved. Thunder was not far away, I think, from this event. So it was just over 2 inches. So based on the actual measurement up here, using that 40% conversion rate, the ASOS, if the sensor was turned on and actually measuring this, would be around 1.2 inches. Again, that's based on that. So when you actually break down the ratios here, they were just slightly under our mean. I think a mean we had a 0.7 to 1 for flat, and then 0.28 roughly for to 1 for radial. So this wasn't far off. So then I actually took the observations and sort of pretended it was in a forecast situation and put it into the FRAM every hour to sort of see, hey, how would the FRAM perform in this situation if it was trying to predict what happened, since we actually have a measurement over here. And we actually came out to 1.515 in flat, which is really point on here, and 0.45 as far as radial. So this was actually very encouraging for Brian and I. So I said, maybe this is a process I can use going back and using ASOS observations to sort of see what some of these major ice storms were in terms of ice. The sensor was turned on. Again, the dissemination of the sensor wasn't until 2013. So when I started going through these observations and calculating the thicknesses using the FRAM, I started to notice the data going missing, and basically the only thing that you could account for that is basically power outage. So we thought, oh, this is great. So I know exactly when the power went out, how much ice actually accumulated hypothetically on the sensor if it was there or in the area. And so we actually found a pattern. Typical liquid, once the power outage actually occurred, was right around 1 inch liquid. So that is a flat ice of 0.52 and a radial 0.21. So you think about that quarter-inch threshold for ice storm warnings that we've been using for years and years and years, and it looks like it's more related to the radial ice thickness. We're approaching that quarter-inch at the 0.21 there as an average, and we started to get damage. But again, this can all be related back to flat ice. So you have the ½ inch there. So another important thing that as I went through these observations, the wind speeds were mainly under 15 miles per hour. Again, we found it typical for these ice storms for the winds to be that low, and so wind wasn't a factor for some of these. So we'd actually found a consistent signal here that we were happy with. So we actually wanted to get some power outage data, again, and relate that to the sensor after 2013. So we came across, we handpicked some of these events here that were kind of notable. There was one in southern Maine there. We were only able to obtain peak outage information for each county with an ASOS in it. But there were a couple storms here in eastern Kansas where Westar Energy was able to give us hourly outage information within a 5-mile radius of the ASOS. So what the conditions were in and around the ASOS, what were the actual outages in that radius. So there's the 2 events for that. There was the big blizzard on the East Coast in January of this year. The Carolinas actually we're in that transition zone, so actually had quite a bit of ice and wind, because that was a pretty wound up system, pretty deep low. But we actually just received this information yesterday from Duke Energy, so we weren't able to actually analyze it, but we know that there were outages in the area, and we know what kind of ice and wind took place. But and another thing we're actually working on is we're currently building a relationship, a partnership here with the Department of Energy to obtain hourly power outage information across the entire country. So they have this large database, and they're archiving some of this stuff, and we're able to pull that from that. So that will most likely help us build a very large, consistent, and diverse data set, making it the process much smoother for gaining this. So in terms of numbers and sample size, we're very hopeful that we can gather a lot of data here to analyze ASOS ice thickness and wind speeds along with this power outage information. So look forward to that. Obviously, when you look at some of the complexities involved with different parts of the country, different tree cover, deciduous versus coniferous, this is all based on geographical location. There's power line mitigation with some of these local power companies. Actually, Westar had a program going here in Hutchinson, Kansas, had an ice storm back in 2009. I believe had similar icing conditions to the storm in November, and they had 70% power outages, which is pretty substantial for a local area. Once you get above about 50% power outage, that's when things become pretty devastating on a local scale. You spread that out over a large area, it becomes devastating and crippling. But anyway, in the storm that happened in November, again, similar icing conditions, they only had 30% outages in that area. So the mitigation almost cut the power outages in half. So that is something that we can't really account for unless we know that information, but maybe it can play into the variability of the data. yeah, and maybe we can get some of this information through the Department of Energy. They're kind of working together with some GIS stuff, looking at how these power cuts are maintained and things like that of that nature. So again, you have the density of the power grid and utility line exposure. Is this a rural area? Is this in a suburban area, or that? Those are aspects that have to be considered, possibly. There's also, when you look at the large transmission towers and distribution lines, there's actually various minimum design loads. We won't get into that too specifically, but based on climatology of ice, some of the transmission lines and distribution lines were actually made to withstand more stress or more ice and wind. So what we were going to plan on doing, if we get a large data set of outage information, was break it down regionally and see if there's differences. You know, does the Northeast vary from the Southeast, from the Plains and the Upper Midwest and things like that? If we do start to see big differences in some of the analysis, then maybe we can start look at some of these complexities and maybe actually, you know, with the help of the Department of Energy and whoever, any partners that want to get involved, break down some of this and maybe have some of a geographically based outage predictor, which I'll try to get into here in a minute. So of the power outage information that we were able to receive here, I've ranked it based on a percentage. So again, this is varying temporal data and spatial data, but there was some pretty good signal showing up. And another thing to note is, you know, your ASOS ice varying as well as your wind speeds. Some of these events had higher wind speeds, and that actually probably contributed to more power outage information or more outages in general. So I'll kind of show you, this is looking at radial ice accumulation versus the outage. There's still a lot of variance here. This is not including any wind. I circled the two at least known mitigation efforts, but what we intend to do is hopefully incorporate, again, wind along with the ice thickness, and hope to have a predictor here of the outages that is much closer here, not a lot of variance that's down the line. So with the hourly information we're able to receive from Westar, we're able to break down some of these observations on this scale. And so on the left, basically I combine total outage percentage and wind gust, and then on the right-hand side you have the radial ice thickness. And throughout the event, you can see at Manhattan here, the blue line is the outages, and they start right around here. So if I were to go up and see, well, what would ice thicknesses when that occurred? It was just around that 0.2 or 0.2 is what we found when we were observing other ASOS 5-minute observations, hourly observations from the past. There's another consistent signal showing up, and you can see the wind speeds started out kind of right around 20 knots, but then decreased over time and didn't seem to really have an effect on it. In fact, if you kind of compare the ice accumulation rate here, it almost kind of mimics I would say the total outage increase here, rate kind of mimics the ice. And then once that stops, there's a little bit of delay, and then the outages sort of slow down. And then here's a more windier event, at least towards the end. It started out windy. And then the winds decreased, but you see the ice accumulated over a long period of time here. Outages started right around here, so if we go up and look, let's see, right around here. Again, maybe right around 1/4 inch of radial ice is when these outages started to occur. Again, right in line with the other storms we were looking at. And another thing to note is the ice sort of stops right around here. We actually have a slight increase in the power outage after that, so a little bit of delay. You can see that the wind speeds increase here, going from like 5 knots up to about 25 knots, and well after the ice has actually stopped accreting, you actually have a bump up here, or a slight increase in the power outages, based probably due to this wind. So something to be considered of when you're in a forecast situation. If you stay below freezing, are there going to be some stronger winds moving in behind this, because you could get further impacts from that storm. This is another windier event here in December in Winfield. Winfield's kind of a small town here, and the wind gusts here were right around 35 to 40 knots, almost through the whole event, and it only accumulated just under 1/10 of an inch of ice. But you had power outages in the area up to almost 40%. So we're not sure if a main distribution line got taken out or something of that nature, but again, hopefully stressing the importance of adding the wind data to this. Otherwise, you would say a tenth of an inch of ice. You guys would be, probably not really expect many impacts, but in fact they did. Here's a breakdown of the North Carolina event. See, the ASOS ice was generally a ½ inch or below, but your wind speeds sustained were right around 20 knots and even gust up to 30 knots there. So you're actually looking at a screen capture that took that afternoon of the outages in place, and the numbers are really arbitrary. It just kind of shows how many outages are in the area, but we know that there were outages. And this doesn't line up with what we were seeing in some of the data that we analyzed, where the wind speeds were lower and the ice was right around ½ inch to 2/10 radial. But this area may be a Rocky Mountain, but generally the other ones are slightly less. I'd actually say maybe Lumberton and Greenville and Florence here, these three were kind of low in ice, but high in wind. So we want to analyze this data and see how much the wind actually affected those power outages. So then we hopefully come together with something like an outage predictor, where you put an ice forecast in, a wind forecast. We have some multiplying factors in there, and then it spits out what would hopefully be a predictor of percentages of ice, of impacts there, the outages. So we actually used a preliminary outage predictor, and we kind of used an arbitrary number. 10% is when you actually maybe start to have impacts that are substantial or actually impact people on a larger scale. So that number can be tossed around, and we chose that for now. So anything that had 10% or greater, we considered it was a successful forecast. We actually took our observations and kind of treated it as a forecast situation, and what did the predictor had, and we kind of related it to some of the other thresholds. So the ASOS ice was greater than or equal to 1/4 inch. Only about 47% actually had a 10% or greater power outages. You're looking at a false alarm rate of 47%. When you move to maybe using flat ice at around ½ an inch and radial being around that 0.2, you actually increase your forecast percentage here to 76%, and then your false alarm drops off to 12. So there's a pretty good substantial improvement in the numbers there. And then when you use the outage predictor, or at least the preliminary one, we had a correct forecast 82% of the time and only a false alarm of 12. So we thought that was really good at least preliminary results to move ahead with this, and hopefully that data set that we get from Department of Energy, we're able to add to this predictor, work around with it, and again, like I said, if we need to do regional analysis and things like that, we can work with that. Maybe even work with local WFOs. You know your area really well. We could always use the expertise, of course, when we're doing this analysis. So always welcome to your feedback or suggestions and things like that. So I won't harp too much on the summary here. Again, I want to stress the additional wind, the different thicknesses, what we actually are going to define in our forecast, how we're going to present this to some of our partners, and we're working on developing the outage predictor, and then maybe this will all work together with the hazard simplification, more of an emphasis on impacts as far as this combination of ice and wind. So that is basically, I think, it. So yeah, there's special thanks to those folks who assisted us along the way with their input, support through the development process, and NWS Topeka for putting up with the many hours and hours and hours of us talking about ice. So we will unmute your lines here, hopefully, and yeah, we'll be ready for questions. Yeah, we're trying to unmute people, John. I don't know if you can chime in.
I've got it here.
Okay, great. So yeah, I think everyone's unmuted, so if you have any questions, yeah, now's the time.
All right, we may have put you all to sleep, which hopefully you enjoyed a good nap. Well, that said, I guess, feel free to email us if you have any thoughts, questions, feedback. I believe all this is recorded, so if you want to pass that along to anyone else who might be interested, feel free. Otherwise, if you have any ideas, we're excited to hear about those too. And like Chris said, anything with your local areas that we should know about, that'd be awesome. Otherwise, check out the SCP if you'd like the tools, and again, holler if you have any questions. Much appreciated. Thanks for joining in today.